A mango, my favorite fruit. It's delicious with a juicy inside and a thin layer of skin protecting it from the outside. How can you mathematically describe the inside of a mango? In this video, you will see how to intuitively think of the definition of an interior point and the interior of a set in n-dimensional Euclidean space using this mango. First, what is the definition of an interior point of a set? Let S be a subset of n-dimensional space. A point P in n-dimensional space is an interior point of S if there exists epsilon greater than 0, such that the open epsilon ball centered at P is a subset of S. Let's apply this definition to our mango. A mango is three-dimensional, but the definition will be easier to visualize with a two-dimensional model. This dough will be our two-dimensional mango. Let me roll it out. So think of this as a set lying inside two-dimensional space. We want to understand how to distinguish the inside of a mango from its edge and the outside. Let's pick 3 different points and place them in two-dimensional space. So I'm going to put one over here, one here, and one right there. Okay. Let's pick 3 different points in two-dimensional space and check if they are interior points of S using our definition. Here is our point A, our point B, and our point C. Look at the first point A. Is it an interior point of S? Intuitively, yes. It is inside the mango. Let's check that the formal definition matches this intuition. So there must exist epsilon greater than 0 such that the open epsilon ball centered at A is a subset of S. This cookie cutter will make an open ball. So I'm going to place it with the point A at the center. Looking inside the open ball, some of it is the mango, and some of it is not. In other words, the open ball centered at A is not inside S. Does this mean A is not an interior point? Not at all. We only need to find one choice of epsilon bigger than 0 that succeeds. So instead of using this open ball, I can place a smaller open ball at A. Right? A should be at the center. Now if I look inside this smaller ball, it contains only mango, my favorite. In other words, this ball centered at A lies inside S. This proves A is an interior point of S. Notice I could have used any smaller ball to prove the same fact. I just don't have a smaller cookie cutter. Before considering the other 2 points, I want to give another perspective on interior points. These cookie cutters allowed us to zoom in on the point A. So a smaller radius means we are zooming in more. So we decided this point was an interior point because after zooming in enough, we can only see mango. This idea gives an informal way to interpret interior points. A point P is an interior point of S if, by zooming in enough on P, all you can see are points in S. Now, let's go back to our 2D mango. We still need to check if the points B and C are interior points of S. Let's start actually with the point C. So is the point C an interior point of S? Intuitively, no. It is outside the mango. To check that the formal definition matches this intuition, we must negate it. For all epsilon greater than 0, the open epsilon ball centered at C should not be a subset of S. So let's test this out. If I put this open ball centered at C, it does not lie inside S. Neither does this small open ball, and neither does this one. So you can see that when I look inside, we've zoomed in so close that there's actually no mango inside at all. In other words, the epsilon ball centered at C intersected with S is empty. This observation means that every smaller open ball will always have empty intersection with S. Finally, is the point B an interior point of S? Intuitively, again, no. It is on the edge. But remember, we must check the definition. For all epsilon greater than 0, the open epsilon ball centered at B should not be a subset of S. So let's try some. So if I put this open ball, it does not lie inside S. There are some points lying from outside S that are sitting in there. Neither does this small open ball lie inside S. And neither does this small open ball. In other words, no matter how much you zoom in, you will always see points outside S. This means B is not an interior point of S. These examples suggest that we can formally define the concept of inside. Let S be a subset of n-dimensional space. The interior of S, denoted S0, is the set of interior points of S. How does this apply to our mango? Recall that we checked A is an interior point of S, whereas B and C are not. Continuing those ideas, any point inside the mango will be an interior point. Any point outside the mango or along the edge will not be an interior point. This means that our intuition matches our formal definition. The interior of S will be the inside of the mango, not including the edge itself. We have also stumbled upon a neat observation. The interior of S is always a subset of S itself. I love it when intuition reveals a mathematical truth. These ideas for our 2D mango work just as well for our 3D mango. The interior of our 3D mango is the juicy, delicious inside. In the next video, we will continue this exploration to interpret the mathematical concepts of boundary points and the boundary of a set using our mango.